Welcome to our second lecture on security and privacy in the IoT. In today's lecture, we'll talk about encryption for IoT devices and the challenges, and about how to enable firmware security. So, what is the requirement for encryption in IoT devices? Now, very often IoT devices collect sensitive data. These might be privacy and or security critical. So, for example, it might be medical data that is collected by your fitness tracker. It might be passwords that are used to access a private wireless network over which the IoT devices communicate, and so on. So what we want is we want to encrypt this privacy and security data on devices, so as long as data is stored on the device, but also while it is processed, transmitted, or received by IoT devices. So we have two challenges. We have data that's on a device, and we have data that's transmitted over the network. Now, of course, solutions for this already exist in the PC and server sector. So what's the challenge for IoT applications? Now, the challenge is that we have to make a trade-off between our typical non-functional properties we need to optimize to enable, for example, wireless cableless operation on batteries or energy harvesting methods for our IoT devices. So reducing the energy consumption, reducing the amount of compute that's required for executing a certain algorithm, or reducing the amount of memory. And even with all these constraints in computing power, memory, and energy, we want to enable strong cryptographic security guarantees for our IT devices. So the questions we need to ask ourselves are, can we enable security and privacy on small IoT edge devices with processors that don't have a lot of computing power, don't have a lot of memory, and usually are pretty low on energy already without cryptographic approaches? What's interesting is to consider the trade-off between the non-functional requirements, and security can be seen as a non-functional requirement, and all the other non-functional requirements like power, memory, and energy consumption, all these play against each other, so we have to find a way to get this to work. And finally, how can we enable secure operation of edge devices also over long time spans? So let's start with a bit of background on cryptography. Of course, this cannot replace any course on IT security and cryptography, so we are linking to one of the standard textbooks that's in use today here. So what's cryptography? Now, it's essentially a set of mathematic techniques, and those, if applied correctly, allow a software developer to achieve or provide a number of objectives or services. So here we noted the four most important services and objectives that can be provided by cryptography. So the first is confidentiality. So this means we want to keep the contents of information accessible to only those persons or computers that we allow to access them. All the others should not be able to read information that is either on a device or transmitted by a device. So this includes, in turn, the protection of all user data transmitted between 2 points over a period of time. But we can also have additional information that can be extracted. For example, we had the example of a light bulb in an IoT smart home application. And just from information about traffic actually flowing between two devices like the light bulb and a router, then we could also deduce some information. So we might ideally also want to protect information that, well, allows us to deduce such meta information. So, for example, the traffic flow. The second objective we want to achieve is integrity. So the data and code stored on a computer and also information transmitted by a computer, especially an IoT device, should be able to be modified only by authorized users. Modification means we write parts of the software or data from scratch. We change it, we change the status of devices, we delete something, we create something new on a device, or we try to delay or replay transmitted messages. So integrity means that an active attack needs to happen on a device. So an active attack means we're connected somewhere to the network and some other person on the network is using one or more computers to connect to our system in a way that we would not support. And if integrity is guaranteed, then all of these attempts to, yeah, essentially connect to the system will fail and will be rejected. And if there's a security problem, as we'll also see in the next lecture, then, well, an attacker might be able to gain access to our system and might be able to change our software, our data, or maybe also eavesdrop on our communication. So integrity protection is first concerned rather with detection than prevention, because we are connected to the internet with our IT devices, so we cannot prevent without having, well, advanced firewalls and other configurations to protect our networks. We cannot prevent anyone to try to connect our devices. And especially in the case of wireless networks, well, the signals are in the air, so we cannot prevent anyone to also inject signals on the same frequency bands. Now, integrity can be provided with or without recovery. So essentially, in the worst case, if we detect an attack, we can try to shut down the system in order to provide worse outcomes, or we can try to defend ourselves against an attack. Objective number 3 is authentication. So we've always talked about authorized users. Now the question is, how can a user actually authorize, so give a system the information that the user is allowed to do what he or she wants to do. In addition, this is also valid for all data transmitted over the network. So authentication means that we can be sure that the origin of a message, which might be a login attempt by a user trying to gain certain attempts or data coming in over the network, this origin is correctly identified. So information delivered over a channel should be authenticated as to its origin, but also correct dates, so timestamps, correct content. So even if the origin is right, the content might be tampered with. So we need ways to ensure that our data content is consistent. And another thing like time of the information processing or transmission. So authentication is thus divided into two major classes. So we have authentication of entities and we have the authentication of data origin. And finally, we want to achieve non-repudiation. So we want to prevent both the sender and the receiver of a transmission from denying previous commitments or actions on a system. So essentially, if a message has been sent out, I cannot revoke it or I cannot tell to the other communication partner that something has never happened. This can be done, for example, by enabling cryptographic signatures on messages added with, for example, consecutive numbers of messages and so on. So when we talk about cryptography, we need to differentiate between two general approaches to cryptography. One is private key cryptography. This is also called symmetric key cryptography, or we are using symmetric key algorithms. And these are cryptography algorithms where the encryption and the decryption is performed with the same key. Or there are also versions where the decryption key can be very easily calculated from the encryption key and the other way around. So the main function of these algorithms, which are also called secret key algorithms, is often a high-speed encryption of data. Now, obviously, we need to keep this identical key secret because anyone who owns the key is able to encode new data and also decode already encoded data that was using this key. So this means that private key algorithms somehow need a way to exchange these keys beforehand. They cannot do it in the open without any encryption. just because then any eavesdropper could just read the key and use it afterwards. So they need a way to do it. So very often in early approaches to private key cryptography, this key exchange took place on a separate medium, for example. So you had something like code books that were transmitted as physical items in World War II already. But of course, this is very cumbersome. So if you need to agree on a key prior to a private key communication taking place, there should be better ways to do this actually. So the problem really is with private key cryptography that as soon as an attacker gains hold of the key, all your previous messages can be decrypted, and the attacker can also generate newly encrypted messages. So if you trust the encryption to provide authentication that the originator of a message is the one you think he or she is, this doesn't work as soon as this key is in the hands of somebody else. So as long as the communication needs to remain secret, and this is also valid in the future, obviously, the key must remain secret. Now for private key cryptography, there's two types of symmetric key algorithms. We have block and stream ciphers. So block ciphers actually work not on single characters, but they always consider a whole block of data. And this makes it very easy to, for example, permutate bytes inside of a block. So move their positions around and also obfuscate their values. This is essentially what block ciphers can do. So a block cipher converts a plain text of a message into a ciphertext by taking a block at a time. This might be 64-bit, 128-bit, so for example 8 or 16 characters, and then it mixes chunks of plain text bits together with key bits to produce chunks of what we call ciphertext, so the encrypted message. And the important thing about block ciphers is that the chunks of ciphertext have the same size, so they're just changed around in a way that hopefully no attacker can figure out. Now, on the other hand, we have stream ciphers. Stream ciphers work on a byte at a time, so they're very useful for network transmissions where you just have incoming or outgoing data that needs to be encrypted independently of the application that produced the data. So stream ciphers convert the plain text into ciphertext character by character. To do this, they cannot mix plain text and key bits because we only have 8 bits per message and the keys are usually much longer. So instead, they generate pseudo-random bits from a key and encrypt the plain text by using an XOR operation with the pseudo-random bits that it generated. And then, of course, it sends the encoded bytes over a communication channel. The other approach to doing cryptography is public key cryptography. So this is based on the idea that we have two different keys. One key to encrypt a message and a different key to decrypt the message. Now, this gives us a big advantage because we can have a public key, as the name says, that's available to anyone who wants to encrypt a message that he or she wants to send to me. But only I can decrypt it using my private key. So we always have a pair of keys that belong together. One is the public key that can be used, for example, to encrypt a message that's sent to me, and that can be out in the open and needs to be out in the open for people to send me encrypted information. And then I have my private key, which I need to keep private, which is the other part of this key pair that allows me to decrypt the encoded messages. So obviously the private key needs to be kept secret all the times. Now, the good thing is the public key is publicly available to everyone, and this includes, of course, possible attackers and so on. Nevertheless, public key cryptography uses mathematical approaches that make it, well, almost impossible for anyone except for the person who generated the keys to derive the private key. So this takes mathematical approaches which are very complex to calculate in one direction and very simple to calculate in the other direction. So usually we rely upon computers being too slow to, for example, derive a private key from a public key in any reasonable amount of time. If you try long enough, you will manage, but maybe it will take 1,000 years. So even if you could decrypt the message, then it probably won't be very useful. So these mathematical approaches are generally distinguished between into three major classes. So first we have algorithms based on the problem of factorizing integers. So we assume we have a large positive integer n, and then we are trying to find its prime factors. So an example for public key cryptography is RSA. This is the most widely used public key encryption algorithm, and this is based on the difficulty of solving these problems. So if you have two prime factors of a number, generating that number is very easy because you just have to multiply the two prime factors. But if you have a large number that, say, uses 1024 bits in a binary encoding, then it's very difficult because you need, in the worst case, to do a brute force attack to find all the prime factors of this very large number. A related approach are algorithms based on the discrete logarithm problem. So here we are given two values alpha and beta, and our question is to find a value x such that beta can be written as alpha x modulo some value p. So for large numbers, this gets as complex as the integer factorization problem. And the discrete logarithm problem is, for example, used in the Diffie-Hellman key exchange protocol. And there are a number of other protocols based on discrete logarithms, for example, the digital signature algorithm. And the most recent approach, though it's also already more than a decade old, is based on elliptic curves. So elliptic curves are actually using the problem of finding points on an elliptic curve of a given formula. So there are standard elliptic curves that are defined, and well, these are the most recent family, but are rapidly gaining acceptance. Compared to discrete logarithm and integer factorization, they have reduced processing needs for encryption and decryption. So elliptic curves, though of course they still incur significant overhead, might be especially attractive for embedded applications like our IoT systems. So the problem is when we try to implement one of these, either private or public key crypto algorithms, how can we make this efficient? We've seen that, well, especially for private key algorithms, there's a whole lot of mathematics required. And even when properly implemented, well, the problem is that they still use energy, they still use computing power and memory. So the first question is, of course, which one should we use? Now, even when properly implemented, all public key schemes proposed today are several orders of magnitude slower than the best known private key schemes. So in practice, what systems do is that they use private key data exchange only for initiating a connection. And then when that connection is initiated, it can be securely used to exchange a private key for private key cryptography. So this means we can combine both sorts of cryptography to get the best of both worlds. Now, the question is really which approaches here exist here to make symmetric as well as asymmetric cryptography algorithms more efficient. And again, we need to consider our non-functional properties like computing power, energy, memory consumption for our IoT use case. And here we have different approaches. One is we try to optimize the implementation in software of our cryptographic algorithm. We have processors that provide special acceleration instructions in hardware to accelerate one or a small class of existing cryptography algorithms. Of course, this probably won't be useful if you switch to a different cryptography algorithm. And finally, there's also hardware coprocessors where a cryptography algorithm is implemented in its own chip as an ASIC. So this can be more energy efficient and faster. So, as we've seen, most cryptography approaches are computer intensive because they have to execute a significant amount of arithmetic and logic operations for encrypting and decrypting messages. So our challenge for IoT devices is, can we actually implement energy efficient cryptography in software? And we want to avoid to compromise security for a reduction, for example, in energy consumption. Now, there's approaches for this. For example, there's an energy variant of the SSL TLS crypto standard proposed in a paper which we link here. However, there is no universally accepted IoT-specific solution for resource-efficient cryptography. This also has to do, of course, that you have to communicate with other devices on the internet. And for example, your servers, your cloud might only be able to talk standard protocols. So if you have a variant of a standard protocol that is IoT specific because it's maybe more energy efficient, but this does not uh, interoperate directly with the standard version, then, well, you cannot expect to have services on the internet really implemented your special version of an IoT-specific cryptography algorithm. So the second approach is to still use standard cryptography algorithms like AES, but to accelerate the critical parts of this. And this is done by CPU vendors. And these, for example, provide instructions to accelerate the software implementation for maybe of AES and SHA algorithms. So this is implemented for quite some time in Intel and AMD processors. And for embedded use cases, there's optional extensions for ARM processors and also for RISC-V. Some of these exist, some of these are proposed. None of these are a required part of the standard, but it would be ideal if also smaller processors would implement them. And as an example, RISC-V splits the instruction set into different optional instruction set extensions. And you see here's a list. All that instruction set extensions have an identifier starting with Z here. So ZKND might be the instruction set encryption for accelerating AES decryption, whereas ZKNE is an AES encryption. And there's more generic features also, like entropy source extension, so if you need random numbers, or also extensions for data independent execution latency. So that means that whenever somebody manages to measure the execution time of your crypto algorithm, then the attacker won't be able to deduce anything useful from it, because these extensions would make it possible that all passes through your software always take the same amount of time, so you cannot actually deduce a key or parts of a key from execution time profiling. So here's an example for the ZKND extension. So as you see, we have separate instructions here for decrypting IAS. So these accelerate the N and decryption itself. They support different phases of the AES algorithms and also special functions of the AES algorithm. And taken together, these can be used to, for example, provide a handwritten assembly version using these machine instructions of the AES algorithms that is much more efficient and maybe so energy efficient and also maybe faster than a pure software implementation that doesn't have these acceleration functionalities available. Now, if you have a CPU that doesn't have support for cryptography instructions, you might also use a special chip that can be added externally to your microcontroller. So there's a number of these hardware cryptography support chips out there that implement one or more cryptographic algorithms in hardware. One example is the microchip ATEC 608B. So this is a cryptographic coprocessor that has a secure hardware-based key storage, so you don't have to provide the chip with a key, but the chip comes with pre-programmed keys, or you can program them once and forever. And it supports a number of cryptography approaches like elliptic curves, SHA, AES, and it also has protected storage for not just one key, but also for 16 keys and also certificates. And essentially, It has hardware support for symmetric as well as asymmetric, public key algorithms. So this is a relatively versatile chip. It's very simple to use, so you can connect it to your microcontroller using a two-wire I2C interface. The crypto support chip itself doesn't take much space. It's just a small 8-pin chip, and it's reasonably expensive. So in single pieces, you have to pay about around $1 at the moment. The big problem with crypto support chips is finding information about them on the net, because this is usually only available under a non-disclosure agreement with the manufacturer that prevents you from putting out more information, or maybe also from putting out source code using these chips. So these might not be ideal if you want to generate an open source firmware or an open source application. Nevertheless, they might be pretty useful. So what other problems do we have? Firmware updates. In the next lecture, we'll see that firmware updates will be critical because very many devices on the IoT are delivered with firmware that has security problems. So we have a requirement to keep the software on IoT devices. So the software that's on a device, we usually call it firmware. We want to keep it up to date. We need to keep it up to date to enable sustained secure operation, even if new security problems with your software on your device are found out while it's operating. And so you should be able to update devices on demand, so not only security. Of course, this would also enable you to add device features to an already existing device that's out in the field. So we have some challenges like updating the firmware over slow and unreliable wireless links. We need to ensure continued operation of devices even when an update fails. So just receiving an update, flashing your flash ROM with a new version, and then rebooting, well, that's problematic because if the flashing fails, you have no working firmware left. So you have to do some sort of version management to check out that you still have one remaining version that's able to successfully perform updates. You also need to ensure versioning, so uh, some things may change between firmware versions, like details of a protocol. So you need to enable networks of devices with different versions of firmware still to interact with each other. And finally, if you have especially wirelessly connected IoT systems, you need to prevent man-in-the-middle attacks. So whenever your device requests a firmware update, this would not be delivered by the original manufacturer of the device, but by someone eavesdropping on the connection and in turn delivering a compromised firmware that has some malware included. Obviously, you want to avoid this. The other problem is firmware security. So very often IoT devices are somewhere out in the field, so you cannot monitor them constantly. So the problem here is that you need to prevent attackers who have physical accesses to an IoT device from, well, even if the attacker takes the device along and analyzes it in his or her private lab, uh, you want to avoid the attacker from reverse engineering the firmware on your system. So the challenge here is how to keep code and data secret, even if the attacker has the possibility to read out your flash memory chips, for example, on the device, and to monitor what's going on. So there are a number of approaches for encrypted flash storage. So this enables secure storage of code and read-only data of IoT applications. And this can take place either by putting the flash on the same chip. So analyzing data that flows on a chip is very difficult. And if you just manage to read the flash, for example, using a debug interface, then you still have encrypted data and you don't know how to decrypt it because you don't have the private key. On the other hand, if you have external memory chips, you can get special versions of these chips that are actually transmitting encrypted data over the bus instead of clear text data. So this needs to be supported by the CPU, obviously, because otherwise, if an encrypted instruction appears at the microcontroller from a flash chip, well, the CPU doesn't know what to do with it, so it has to be decoded, decrypted first before it can be executed. So there's usually always a way to attack systems because there needs to be unencrypted information somewhere in the system, for example, to execute instructions or to operate on data. There is one trend which is interesting but currently not practically feasible, called homomorphic encryption. And that means that we can actually devise algorithms that directly work and manipulate on encrypted data. So, for example, you could build an adder that, well, usual adder adds two numbers and gives a result, obviously. And this adder would take two encrypted numbers and produce a result that would be the encrypted version of the two, well, operands that you pass. So the interesting thing is that with homomorphic encryption, this can happen without having to decrypt the numbers. So this uses knowledge of the encryption algorithm in order to directly perform this operation on the encrypted numbers. Now, the problem with this is there are working approaches, for example, by IBM or Dresden Technical University. However, these are very, very slow, like in a factor of hundreds of thousands or a million slower than using regular cryptographic algorithms. So this needs more research to be feasible. So additionally, you want to enable security in hardware. So one idea is to just put all the critical operations in a special compartment on your processor that is somehow shielded or isolated from the rest of the software running on it. So even if somebody manages to inject malicious code onto your regular firmware, then something like private keys might still be protected in this security environment. So this is an additional method that helps to protect a system from attackers. And what this does, it implements a so-called trusted execution environment. So this trusted execution environment is a secure area of a main processor, and it guarantees that code and data loaded inside this trusted execution environment are protected with respect to confidentiality and integrity. So they are not leaked to the outside of the TEE, and they cannot be changed except for inside the TEE. So the trusted execution environment provides a number of security features, and these include isolated execution, the integrity of applications that execute within the TEE, and also the confidentiality of their assets, so the data they operate upon. And so typically we try to reduce the size of what we call the trusted computing base that runs inside of the trusted execution environment, and this is often used for content protection. So if you have encrypted video or audio files, mobile financial services where you need to prepare transactions for online banking, for example, or authentication services. Now, trusted execution environments require hardware support, and this is readily available, for example, in ARM processors using the Trust Zone technology. And this provides barriers and also defined interfaces between trusted and untrusted regions of the code on a system. So that means we have, for example, a functionality to encrypt a message inside of the TEE, and there's a defined interface where we can put in clear text and receive the ciphertext back without actually knowing what's going on inside of the TEE. So it's a separate software component. And very often this, feels like an operating system, but it has very special features, usually related to security, and the remaining operating system functionality can still be implemented outside of the trusted execution environment. Now, another recent interesting development is that you can actually try to enable security in system software. Now, that first sounds like, I don't trust this, right? Because you've all seen the number of security holes in classical operating systems like Windows, Linux, and whatever. So the idea that some researchers in Australia had was to have a kernel that's very small, and that would then enable a formal verification of features of this operating system to ensure its security. So such a formal verification is a mathematical proof that the implementation of a system, so for example, the C code implementing your operating system kernel, conforms to a given specification. And when you have successfully verified this, this implies, of course, if your specification is correct, that your implementation is free of bugs such as deadlocks, live logs, buffer overflows, arithmetic exceptions, use of initialized variables, and so on. So all the typical problems that might lead to either a denial of service or a security hole, for example, through a buffer overflow on the stack. And to ensure that this verification was actually feasible, the Australian researchers based their research on a project they've been working on for a long time, the L4 microkernel, which was originally developed in the 1990s in Germany by Jochen Liedtke. And they built a special version of the L4 microkernel called the SEL4 microkernel, which they managed to verify formally. So this was developed since 2006 in Gernot Heiser's group at UNSW and NICTA. It's very interesting to read his blog to see what can go wrong in research, especially when you require funding and have very sensitive things that you're working on. And this verification started from an executable specification that was written in a functional programming language called Haskell. And this was obviously much more simple than the C code of the kernel. And the verification was completed in 2009 for ARM processors. So the SEL4 kernel is intentionally kept small. It's a so-called microkernel because most of the functionality that a typical kernel like Linux, for example, has in kernel space, like device drivers, but also some things like memory management are moved into user space. So there is already a protection barrier between the kernel running in privileged CPU mode and the rest of the software running unprivileged. And the remaining small part of software remaining privileged mode is what has been verified. And this is relatively small, so SEL4, the kernel consists of about 10,000 lines of code. And if you want to take a closer look at that, it's open source, available from sel4.systems. And if you think, well, that's maybe a very exotic development, maybe you already own an SEL4 device. So the baseband processor on all iPhones and the T2 security chip on all Mac CPUs, well, this is running SEL4 under the hood, though you don't know it, right? Because these are systems you usually don't interact with. So you don't see a user interface or a shell or something of SEL4, but it's just running as an embedded piece of software under the hood. So maybe you already have one SEL4 system running, but still, if you want to use it in your applications, it's out there, you can use it. And there's also ports to other platforms like RISC-V, for example. So let's conclude today's lecture. Security is still a critical missing feature of many IoT devices, and we'll show a number of examples for attacks in the upcoming lecture. So our final lecture on security in the IoT. There are a number of approaches to ensure on-device and data transmission security, but we've seen that using traditional approaches that are supported on the internet or on the cloud may run counter to the non-functional parameter requirements or constraints of IoT devices, such as energy, memory, processing power, or also cost, of course. Considering €1 for an external crypto chip might be a significant part of the cost of a device. And we want to avoid any trade-offs between the achievable security and non-functional parameter optimization. And so we can try to approach the problem in the several ways represented, from optimizing software to using special instructions to using special chips to adding security on the software side, for example, by using formal verification or trust zone support. So this is all important. This in itself is, again, a very complex topic, so we can only give some links and hints, but I hope you found it interesting. So here's all our links to related literature as always. So thanks for listening, and until next time, bye.